Okay, and we're recording. All right, welcome back, everybody. Today, I want to say at the end of the last class, the last class was a massive class where we covered tons of material, right? We whipped through like three big new ideas. And normally I cover like one new idea every 2 days, and I whipped through like two big new ideas. I whipped through displacement current and changing magnetic fields, creating electric fields, and changing electric fields, creating magnetic fields. And there are a couple of questions on the homework on those problems, but those by themselves are not the most important thing, because the real reason they get us anywhere is they get us to the top of the mountain. So if I so the view from the top of the mountain now is we've got a set of equations that describe electricity and magnetism fully. We have Gauss's law. We have, for lack of a better word, Gauss's law for magnetic fields, right? And this one is the one that tells us that magnetic fields loop and that there are no magnetic monopoles. So this tells us where there's smoke, there's fire. And then the two more interesting ones, Faraday's negative d flux dt and Ampere's law, mu naught epsilon naught the electric flux dt. So this is the version of Ampere's law where we don't have any actual real current, and this is the displacement current you get from a charging capacitor. Right? Now, these laws, and in particular these constants, will show up here, and they also show up in magnetic force. Those are all things we can measure, right? We can go to we can measure epsilon naught, for instance. That's Coulomb's constant, because 1/4 pi epsilon naught is equal to the Coulomb constant. That tells us that's the strength of the electric field, right? The strength of the electric force. We can measure this by measuring the force between two charged objects. Mu naught we can measure by measuring the force between two current carrying wires, right? If I have two wires near each other, they'll attract or they'll repel, and we can measure that. In fact, that would be one of the measurements we would have done in lab had we not had COVID hit, is we would have actually done that exercise. It's a fun exercise. So this is, as I was saying, like, this course is not an easy course. And the reason is because electricity and magnetism are not easy to understand. They're coupled ideas. There's commonalities between them, but these are like not easy to get to. And they're not easy once you're here. So at this point, we've reached the peak of the mountain, right? We've done all of the heavy climbing, and now we're at the top. And so I want to spend a few minutes just examining the view, right, before we start our descent on the other side of the mountain. Now, going down a mountain is not trivial. You can trip and fall, and there's still, it still takes some work, but it's a lot easier than climbing the mountain. So we've done the hardest things in the course, I think, at this point. There's some things left to do, but I think they're relatively easy in the next couple of weeks. These are topics that most people feel less worried about, more confident in than they do the other topics. So we're past the hard part, and we're on binder number 3 of my notes. So we're not going to get through that whole binder. So now, as I was talking about, so the conclusion from last time was what happens if we put these guys together. And in particular, Faraday's law and Ampere's law, these two talk about magnetic fields and electric fields and magnetic fields. So we can put these two together. And so what I want to do right now is offer, well, basically some bullshit. All right, so what I'm about to do is wrong in every possible way, but it's demonstrative of the idea of chapter 32.1 or 32.2, I forget which one it is, 32.1. I'm basically going to repeat the argument, but do it really, really stupid. And if nothing else, this is just a dimensional analysis. It's just telling us something about units. But I find kind of tells the story without having to go through all the details. And this is like this. I'm going to say a DL I'm just going to call that a dx. That it's a length, right? It's a small length. And what I'm going to do is I'm going to break these integrals in this formula and this formula down into infinitesimals. So I'm going to write this as dE dx equals negative d by dt. And another thing I'm going to do is a flux, so for instance, the magnetic flux is equal to b times a. And so I'm going to write that as an infinitesimal. I'm going to write that as dB dx squared, right? Because a small area is dx squared. So I'm going to just write this thing as dB, or I'll write d flux is that, as dB dx squared. So I've substituted field times area in for the flux here. And I'll do the same thing on this formula on the right. I'll say dB dx is equal to mu naught epsilon naught. And I'll do the same thing here with electric flux. I'll say this is dE dx squared over dt. And then what I'm going to do is I want to get rid of the B fields. I don't want to deal with B fields. So what I'm going to do is I'll take this guy and substitute him in here. There's one dx on here already. So what I'll have is I'll have negative d by dt dx. And then I'll have all of this stuff substituted in for, so I'll write this as this and substitute this guy in. So what I'll have is mu naught epsilon naught dE dx squared over dt, and that's equal to dE dx. And I'm actually going to ignore the minus sign as well. It's not really, it goes away when you do everything the right way. I'm not doing things the right way. Again, this isn't complete bullshit. So let's drop those dx's. And let's move this dx down here. So I'll have dE squared dx squared, or d squared e dx squared is equal to mu naught epsilon naught 1 d squared e over dt squared. All right, so I've got a dt squared on the bottom here. I bring this dx squared down to here, right? And so I have second derivative with respect to position equals this second derivative with respect to time. Now, we didn't spend a lot of, and here I've specifically said that the electric field is a function of space and time. I'm allowing the electric field to change over time, and I'm allowing it to be different in different places in space. And here, in fact, the electric field should be a vector, and I'm just kind of ignoring that. I'm just kind of letting that go by the wayside, because really what I'm interested in here is the dimensions. This is a second derivative with respect to space. This is a second derivative with respect to time, and this is the wave equation. This is what we were doing back in the very first thing we did in this course. We briefly reviewed simple harmonic motion for like a day, and then we went on to waves. This is a wave equation. Now, at this point in the course, you should understand why we did waves this time, is why waves fit in with all this electricity and magnetism. It seemed like a really dramatic break, but oh, this is why, is because it comes back here. So this is a wave equation. It describes a wave where E would be the amplitude of the wave, or E is the displacement of the wave at some particular time. And it works in distance and time. And this thing tells you the speed of the wave. So if I look at the units of this thing, so the units of E will cancel. So the units of mu naught epsilon naught have to be something like dt squared over dx squared, right? If I bring this up here, it has to be those sorts of units. So if this has to be in seconds squared per meter squared. All right, well that means if I flip it, 1 over mu naught epsilon naught, that would be in meters squared per second squared. And so if I wanted to get a speed, 1 over root mu naught epsilon naught would be in units of meters per second, which is a speed. Now, just to play some funny games here, so what this tells you is that the speed of this wave, which is in fact the speed of light, is 1 over square root mu naught epsilon naught. And what you can do is you can calculate this. Remember, this is a number we could measure by looking at 2 wires carrying currents. And this is a number we could measure by rubbing some sticks and measuring the force between them, right? So if we make those measurements, we actually know what those numbers are. We know that mu naught is 4 pi times 10 to the minus 7 in whatever units it's in. And we know epsilon naught, well, the easiest thing here is 1 over 4 pi epsilon naught is equal to k. So epsilon naught is equal to 1 over 4 pi k. I like using k better. So let's put those in. So that's 1 over root 4 pi 10 to the minus 7, 1 over 4 pi k. Well, this is pretty handy. The 4 pi's disappear. And I have 1 over root 10 to the minus 7 over k. K is 9 times 10 to the 9 coulombs per whatever, newtons per whatever coulomb squared. So this is 1 over square root of 10 to the minus 7 over 9 times 10 to the 9. So that's equal to the square root of 9 times 10 to the, let me see, 9 minus 7 is 16. So that's 3 times 10 to the 8 meters per second. Then what you can do is you can go measure the speed of light. And there are a lot of techniques for measuring the speed of light, and they are really cool. We do some of them in some of our advanced labs, but this was actually done in the mid-19th century, before there were lasers, before there were like high-speed clocks. There was ways that you can make this measurement just with gears and levers and mirrors and a bright light. And you can measure this. And so if you measure this guy and you measure this guy and you measure this guy, you find this relationship holds. The experiment agrees with this. And this is very important to point out. We didn't prove that the speed of light is 3 times 10 to the 8 meters per second. What we did is we said, if we measure the speed of light and we measure these two other things, they agree, which means this theory, even the non-bullshit version, got validity to it. Of course, you can never really prove anything in science. Science is a game where you eliminate impossibilities. You eliminate theories that don't work, and the ones that survive and are strong, sometimes you have to tweak them a little bit to make them right. Like we have to get the value of k just right, or have to get the value of mu just right. But basically, these are the theories that survive. And so this theory, the electromagnetic theory, is now very strongly proven. Just that piece of evidence alone, that we can predict the speed of light and measure it very accurately, tells us that this theory is right, that we're on the right track here and we're not barking up the wrong tree. So, not that you guys would disbelieve me, but this is why this is such an important moment for science. So I had you guys do this reading, go through that reading, and I just like, give me that overview of what happened. And I just want to briefly mention this. So what are the input ideas? What went in? When either electric or magnetic fields vary with time, they induce a field of the other kind, which are the rules for Ampere's law and Faraday's law. Or is Maxwell's equations describe the basic principles of electromagnetism? Yes, that's what we put in. That was our input. And then what are the outputs of this argument, of this mathematical argument they made, of which I just did a toy version, like the BS version. So one of the major conclusions is that the speed of light is this, that this predicts this. But there are several other predictions that happen along the way. And in my BS version, I can't really do this. But these are very important parts. So Mac and Cheese says, electromagnetic radiation is a transverse wave. There's a ratio between the electric field and the magnetic field. The two are related. The wave travels through a vacuum. They require no medium to travel. All of those are huge parts to this whole thing. And I want to talk about each one of these things in turn. So the first thing, let's just, not in turn, but let's do this in some slightly different orders here. So every wave has a medium, right? If you push on water up and down, the water travels along. Now the wave is the water being low and high and moving along as you move the water up and down, as you splash your sister in the pool or whatever. That creates that disturbance. And the medium is the water, or maybe the water-air interface. If I talk at you, the medium is sound. If I'm sending this Zoom meeting to you, there's waves traveling along the electric wires that run from somehow from my house to your house carrying information, that those are electrons that are moving back and forth. It's a charge wave, something like that. Now, in the case of light, the medium is what we just described. It's all those rules we just described, which are electricity and magnetism. So the medium is the electric and magnetic fields, those fields. Now, remember when we started out, we said electric field, well, it's just this kind of trick you can get so you don't have to keep track of the charges. Well, it turns out it's a real thing. The electric fields and the magnetic fields are actual physical things. We can't touch them, but they have very, very important mechanisms. And so you can travel through vacuum of space without needing any air to jiggle around. Now, if it's in air, the air does jiggle around, and that changes the way the electromagnetic wave works. You can have light travel through glass, and the glass changes how the light travels, because one way of thinking about it is that the values of mu naught and epsilon naught are different in different materials. In a different material, these have different values. For instance, the epsilon, that's like the dielectric constant. When we were putting bits of plastic in capacitors, we could find that we could change epsilon naught. So a dielectric constant could change that. So if I'm going through different materials, I'm changing the way electric and magnetic fields talk to each other. And so I can change the speed of the wave or maybe some other characteristics of the wave. So this is one of the really important things, is what's light travel through? It travels through nothing. Now, this was in fact a very big sticking point coming up to the 20th century, is at the time that Maxwell came up with all this, the dominant theory was, well, there's a thing, it's traveling through, there's always had to be a thing, and the thing is this invisible mesh, this invisible stuff which permeates everything, called the ether. This is called the luminiferous ether, luminiferous for light. It's the thing that light travels through, this luminiferous ether, and it must extend through all space. It's this thing we can't touch, but must be sort of everywhere, and it's the thing that lets the electromagnetic waves go through. This was had a big role in discussions about relativity, and it turns out to be total nonsense. You don't need such a thing. You do need to have the existence of electric and magnetic fields, but electric and magnetic fields are themselves a little bit subject to observation. What looks like an electric field to you might look like a magnetic field to me, right? If I've got a charge here, it looks like it's creating an electric field. But let's say I am standing on the back of a truck that's traveling along very fast with this little charge. Well, to you, this charge has been traveling, so it's generating a current. So it's creating a magnetic field. And its magnetic, so its electric field looks different to you, and it looks like it has a magnetic field, but it doesn't look like it has a magnetic field to me. This is actually one of the big inputs into Einstein and the development of the theory of relativity, which we do not have time to get into. It's a lovely, lovely subject, and we just do not have time to get into it. It's really, really cool. It's effing cool. Okay. The other part of this is that electromagnetic radiation is a transverse wave, and that is important, and that comes out of the more sophisticated proof, not the BS proof. But what that tells you is what an electromagnetic wave has to look like. It tells you, let me see if I share. Boom. That what this looks like. So in this case, the electric field is in red and the magnetic field is in blue. And it tells you that if the electric field is going left to right and the electric field is going up and down, then the magnetic field has to be going left to right if the wave is going along the z direction. So in this case, the z direction is along this direction of the wave propagation. This is called a plane wave. There are other things, there are other variations that you can have on these waves in the same way. So this is like a wave where I've made a wave tank like in a trough, and the waves are all traveling in the same direction. So this is like waves coming in from the ocean. They're all aligned with each other. You can have other kinds of waves, like in a pond, I could have something moving up and down the center of the pond and it makes circular waves that travel out. In electromagnetism, you can have, that means spherical waves. So I can have waves, and those are the waves you would get from from a light bulb. They would make spherical waves. We're not going to talk about all those. That's a fairly sophisticated topic. We're going to concentrate on this version, which is what light looks like if you're far away from the source. It kind of looks like this. You're seeing this. Now, of course, this black line down the middle, there's many, many of those black lines. They're everywhere, right? And there's nothing actually moving left and right and up and down. That vector is just illustrating the field, the direction and the strength of the field at every point along that line. So I could draw lots and lots of these all next to each other. But this tells you what the thing looks like. Now, one of the rules for this, it turns out, and one of the outputs of this, is that the electric field has to be perpendicular to the direction you're traveling. That the electric field has to be perpendicular to, I don't know, like I'll call it the V vector, what direction that the wave is traveling. Also, the B field has to be perpendicular to the direction it's traveling. And in this particular solution, we also have the E field is perpendicular to the B field. And in fact, there's a rule called, there's a thing called the Poynting vector. I think I'm writing this down right. And this tells you the direction of which the wave is traveling. This is the direction of the electric field and the direction of the magnetic field, and that's a cross product. So it tells you if the electric field is going this way and the magnetic field is going this way, E cross B tells you that this has a velocity that's out of the page if this is the situation. So in fact, you don't have a complete choice. There's sort of, this tells you the handedness of how these fields go. Bizarrely, this vector, which points along the direction of the field, is actually named after somebody named Poynting, which is kind of bizarre, but true. Let's see where it's going. Here we go. This is not an important detail, but it's it came up just briefly when you guys were discussing which way. So I asked you, if I have an electromagnetic wave traveling in the plus x direction, what directions can the electric vector take? And somebody said, well, it can move in the plus x direction or the plus z direction. It can move in the plus y or minus y. Trying my best says it can go in plus x, plus y, minus y. And this is actually closer to true. So if for instance, if I have my wave is coming at me, that means the electric field could be pointing this way, or it could be pointing this way, or it could be pointing this way, or it could be pointing this way. But it could also be pointing, and nobody mentioned this, it could also be pointing in any of these directions. Any of those directions is fine. I could rotate this picture I've got so that I could rotate this. It could look like this, or it could look like this, right? All of these all give me a ray that's pointing outwards. That is to say, I could take my picture and I could rotate it on its axis and it would still give me the same result. The nature doesn't know anything about the x-axis. So I could rotate the whole thing. The other half, and did I print this out? I'm not sure I printed it out. Yeah. So the other half, if you understand the Poynting vector, then that actually tells you if you pick one of these, what the answer would be. So for instance, Trying My Best actually got this right and Mac and Cheese didn't get this right, but this is not very important. I don't want to belabor that. It's not really an important fact in all of this at this level of understanding. But it does mean that the electric field can point in one of many different directions, and that's one of the really important things that we're going to talk about later today. Before we get there, though, I want to just point out a couple more things about this. One is that we know waves carry energy, right? And in fact, if you remember for strings, you remember back at the beginning of time when we started this course, back when I was 30 years younger, was like M over L V F squared A squared. This was the expression that told us the amount of energy that you're pushing down a string, the amount of energy, the power that you had in a wave, how much power you had to put in to wiggle a wave. It was traveling with some frequency and some amplitude. Well, in this one, we've already shown in this course how the energy of electromagnetism, if I have an electric field, that's proportional to the electric field squared. And it's another one I didn't have time to talk about, and I sort of skipped over, is that the magnetic field also stores energy, and the magnetic field also stores energy proportional to B squared. So that means if I have a wave, the wave has an energy that's proportional to E squared, so the power is also going to be proportional to E squared. And the same with B squared, and since E and B are related to each other, this is the same thing. In fact, in an electromagnetic wave, half of the energy is always contained in the magnetic part, and half the energy is contained in the electric part. And you can think of it as trading energy back and forth. So what this means is that if you double the electric field that's creating your light, you quadruple the power. And the power is what we perceive as the brightness of light. If we see light and it's brighter, that means it's carrying more energy. And so if you double the electric field, that means you're quadrupling how much energy the thing is carrying. In the same way that when I had a string, and if I double the amplitude, I'm quadrupling how much energy I have to put in to making the string wiggle. This, right? This is one of these beautiful things about physics, is two completely different things. Wiggling a string up and down and the interaction of electromagnetic fields basically give you the same story. They basically give you the same thing. So this tells you that E is the amplitude, or we could use B instead, but E is just easier to talk about, that E is the amplitude of the wave. So the solution to the wave equation is that I can have E of x and t is going to be equal to some amplitude times cosine kx minus omega t is the solution, just as we had as the solution to the wave equation when we're dealing with bits of string. Hey, that's cool. I'm going to come back. I have to put vector signs over this because this is a vector. So which way is the electric field pointing? So this thing's got to know which way is the electric field pointing. I'm going to come back to this, right? So can anybody tell me what K means in this equation?
Isn't that the wave number?
It's the wave number. When that tells us what? What's the more common thing we talk about? The wave number gets us to what?
Wavelength.
Right, the wavelength. Right, and what's omega tell us?
Is it the frequency thing?
Yeah, that's right. This is the angular frequency. That tells us F, the frequency of the wave. And these two are related, right? We're not allowed to pick any K and any omega because those two together tell us how fast the wave is going. In fact, one way you could put it is that F lambda is equal to C. So I could write this as cosine 2 pi x over lambda minus 2 pi frequency over period. 2 pi, sorry, product 2, yeah, I can just write it like that. Or 2 pi f over t and f times t, right? And that gives us to this thing. So this number and this number are related to each other by the speed of the wave. And we know the speed of the wave is dictated by the medium. It's dictated by how electricity and magnetism interact with each other. But these two numbers, so if I pick a certain wavelength, I know what the frequency is. Or if I pick the frequency, I know what the wavelength is if the light is traveling through some medium. So, you know, if we're looking at a piece of wave, right, the electric field here is pointing like this, and it's 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 pointing like this. So this, we're just looking, for instance, here at the electric field as this is traveling along. We can, for instance, measure the wavelength of that light. So the wavelengths for visible light are, so for red light, lambda is something like 600, 700 nanometers. For green, lambda is, I forget, it's like what is it, 550, 530. For blue, lambda is something like 420 nanometers. These are kind of crude numbers. I'm just doing this off the top of my head. Light that's has a longer wavelength than about 700 nanometers. And I remind you, a nanometer is 10 to the minus 9 meters. So it's 1,000 times smaller than a micrometer, which is 1,000 times smaller than a millimeter. Anything that's longer than this is infrared. We can't. Our human eye isn't subject to it. Infrared's used for lots of things. It's used for your television remote control. Stuff like that. It's used for reading compact discs, CDs, DVDs, all use infrared light. If it's shorter than about 400 nanometers, your eye can't perceive it, and we call that ultraviolet, and that's used for a whole bunch of other things. It's the light that comes from the sun that gives you sunburn. It's the wavelength in which insects see, stuff like that. So, and then if you get to even longer wavelengths, you get out to radio, as I briefly showed last time. If you get out to very long wavelengths, you get out to radio waves. Microwave ovens are somewhere in here. Shortwave radio is used for very long-range broadcasts. This is what you use for television and TV. These are very long radio waves. We use them sometimes in radio astronomy. If you get up above ultraviolet, you get into X-rays and gamma rays. X-rays being the thing, you know, you get an X-ray picture taken, and gamma rays being high energy rays that come out of nuclear decays. X-rays come out of atomic transitions, and visible light comes out of chemical transitions. Okay, all my notes are a complete mess now. Okay. Now, white light, right? So what's coming out of your screen and hitting your eye is some combination of all of these. When we talk about white noise, for instance, we're talking about static, which consists of both high and low frequency components. In pure white actually means even numbers of all that stuff. For white light, white light is actually a combination of all these lights that come at you at once. And just to be, you know, sort of clear about how basic things work, if I have something that is, if I have something that is red, what's happening is that white light from the room, from the lights in the room, are coming down and hitting the red pen, and then the light from the red pen, light reflects off the red pen and comes back to our eye, but the red pen is absorbing all the wavelengths that aren't reddish. There's only a few there's only some set of wavelengths that this thing actually reflects, and those come and hit our eye, and the rest of them get absorbed by the pen, and so we can't see them. You have a similar thing is if I have like a piece of translucent green plastic and I shine a light through it, the light is green. And what this is doing is anything that isn't green is getting absorbed. Green, or at least some of it is getting absorbed. Green light is some of it's being transmitted and some of it's being reflected. So it looks green because some green light bounces off it to our eye, and also it lets green light through, and so it can do that. And a lot of materials have that property that the same light they transmit, they also reflect. And there's reasons for that, but that's one of the things. So that's what color is. Color is wavelength. Now, to get to the fun stuff. I've been talking at you too much. I need to get to a concept test here soon, or everyone's gonna fall asleep. I'll lose my cred as being an interactive teacher. All right, so let's go back to this notion that the electric field can point in any direction. So if I have a wave that's headed towards me, the electric field could point in any direction that I wanted it to. Now that direction, right now, so for instance, if this wave were coming towards me, what would be happening is the E field would be doing this. It'd be going back and forth along that line. Sometimes it'd be pointing that way, and sometimes it'd be pointing that way, right? I'm just picking one moment in time to show which direction the E field is, but it'll be going back and forth along that line for that whole time. So in fact, an E field that's pointing this way and an E field that's pointing this way are in fact equivalents. It's the same wave, I'm just looking at it at a different time. It'll have all the same characteristics. But a wave that's pointing this way and a wave that's pointing this way might have different characteristics, and in fact they do. And what we call this the polarization of the wave, is which way is the electric field pointing, right? Now, you can actually select a polarization by making a choice. Now, you can do the same thing with a piece of rope, right? If I have a piece of rope, I have transverse waves on a piece of rope. I could wiggle the rope string up and down, or I could wiggle the string side to side, right? Both carry waves down the rope. They're both the same. But if you imagine a rope, right, what I could do is I could take a piece of wood or a piece of cardboard and carve a slot out of it, okay? So when I do this, it allows so if I jiggled the string up and down, that wave would continue right through that slot and not have a problem. But if I jiggled the string side to side, it would hit the sides of the slot and I'd lose all my energy. And so I wouldn't get I'd get very little wave propagating out through the other side of the slot. This is what we call a polarizer. This is a string polarizer, which is a stupid name for a slot in a piece of wood, but that's what it is. It selects only one polarization. Now, here's the other question, is if I wiggled the string instead of straight up and down or straight side to side, if I wiggled it sort of at an angle, right, what would happen on the other side? What would I get on the far side of that slot if I jiggled it? So here's my slot, and if I jiggle it like this, what am I going to get on the far side? Will I get anything?
Force the the Y portion of the diagonal to go away, and it'll just be straight, just with a less magnitude.
Yeah, that's right. So it'll be less magnitude, and it'll be going straight up and down, right? Because the slot pushes on it and forces it to be straight up and down. Only the up and down part survives, so it's smaller, and the side-to-side part gets canceled out, and so what's coming at is up and down. So it does two things. It both reduces the amplitude of the wave, and it changes the way the wave is pointing. So after it's come through the slit, it'll only be moving up and down. It won't be moving side to side at all, or hardly at all. This is exactly the same principle that applies to light. So you can do this by creating a material, and what you do is you take a material that's like a plastic, you warm it up a little bit and then stretch it, and so all the plastic molecules, the long chain hydrocarbons, align with the stretching direction, and that creates kind of a grating effect. So it's like having lots and lots of slits. That's the modern way in which one makes a polarizer. There are other ways of doing it as well that are very, very difficult, but that's kind of what a modern polarizer is. And if you do this, you can shine a light through it, and the light becomes polarized. Now, of course, natural light is polarized in all directions sort of equally. But after you run it through a polarizer, it'll be running only up and down. I could be wiggling my string in all sorts of crazy directions on one side, and what will come out through the slit is only waves that are going up and down. So a couple quickies here. This is basically just an opportunity for everyone to turn their cameras on, right? Yeah, so it's going to be C. It's going to be about the same. There might be a little bit of loss. If this filter isn't perfect, I might get a little extra loss, but it's basically going to be the same amount, right? What am I going to get if I do this? Yeah, so some of you are answering B and some of you are answering C. So Calvin, why are you saying B?
Just because it's turned like halfway, so it's like turned 90 degrees. So
Well, here's a question. If I took two things and I turned them 180 degrees, how much light would come out?
the same.
It would be the same, right? So it's going to be maximum through, and so if I'm halfway, it's obviously reducing it, right? And then their answer is these are perfect polarizers, is going to be none, right? So if let's say I'm wiggling my string up and down, only up and down survive the first filter, but the second filter is horizontal. So nothing survives the second filter. If these two guys are directly up and down and directly horizontal, right? Which is maybe hard to see in the picture. Now, I don't know, how many of you guys have gotten your kits from, some of you?
I still need to get mine.
Okay.
I got mine.
Well, in your kit is something like this. It's a gray piece of
Yeah.
plastic. It was in a wrapper. And in fact, it had a film on it that you can peel off to make it a little bit more transparent. And this is a polarizing filter. And you can see what it looks like is it just looks like it's just blocking some of the light from the white paper. I have a pair of sunglasses here. A pair of sunglasses do something similar. Let me see if I have some. If I have some light, these are just the old sunglasses. It just blocks some of the light. And this also seems to block some of the light. But they operate differently. The sunglasses, at least some sunglasses, block just all, they just block some of the light. They're just smoked glass. They absorb some fraction of all the light. Otherwise, they do nothing. Polarizing filter, though, it takes off the light, but it only takes the light that's polarized in one direction. Now, let me see if I can. So we got a flashlight here, and I blacked it out a little bit. Let's reduce the exposure. So I've got another piece of polarizer here, and depending on how I put that polarizer, if it's this way, it does almost nothing. It does, in fact, nothing, because the first, so for instance, if the first polarizer is polarizing the light up and down, and this guy's also polarizing the light up and down, well, everything makes it through. Everything that made it through the first filter will also make it through the second filter, because it's all polarized up and down. If I rotate it 90 degrees, very little of it makes it through. And if you do this with the, and you can do this yourself. So if you take one of these squares and cut it into quarters, so cut it into 4 quarters, you can do this yourself. And you should absolutely be playing with this. If you don't have it yet, when you get it, take it out and play with it. It's great fun. So now in between, of course, so in between, very little light making it through. If there was a perfect polarizer, 0 light would make it through, but these aren't perfect polarizers. Getting perfect polarizers is very hard. But it's very close to it. That way, nothing's making it through. And that way, everything that makes it through the first one also makes it through the second one. And of course, somewhere in between, I get more or less. Now, what we can do is we can work out how much light we're going to get depending on what that angle is. And that gives us something called Malice's law. And this is really, this is neat because it uses everything we know so far about light, or some of the things we know so far about light, to tell us what's going on. So let's say I have, after the first filter, let's say the light is polarized in some direction. So the light is coming at us, and it, let me change the exposure again so we can see everything. So let's say the light is in some direction, and I'll call this the x-axis. And let's say this E is going to be some EX in the I hat direction plus some EY in the J hat direction, right? So there's EX and EY. It's a vector, so I can decompose it. So in this case, the ray is headed in the Z direction towards us, right? So I can write this down. This is E1X, E1Y. I'll call this all E1 because this is the light after the first polarizer, okay? So then I'm going to put it through a piece of polarizer. So this is before, so this is after filter 1. That's what the light looks like. It's something like that. So then I want to put it through filter 2. What I'm doing is I'm going to put filter 2 to be horizontal. So that's in the I hat direction, in the X direction. So what does this guy do? Well, he does 2 things. The first thing he does is he takes out only the component that's in the X. It takes out only the horizontal component of this guy and leaves nothing else, and then puts it in the horizontal direction. So the field at E2 is going to be in the X hat direction. It's going to only be wiggling left to right afterwards. And then it's going to have E1 dotted with I hat. And what this operation is called projection. It's like take the stuff, but only the stuff in the I hat direction. And what that means is I hat dot I hat is 1, I hat dot J hat is 0. This just means take the X component. So this is going to be I hat times E1X. Okay, that's fine. Now if I rewrite this using an angle in there, so here was E1, and this is angle theta, then E1X is going to be equal to E1 cosine theta, good old trigonometry from our first semester, right? All that good blocks on slope stuff coming back. So this means E2 is going to be equal to I times E1 times cosine theta, where this is the strength of the field after the first filter, and this is the strength of the field after the second filter. If I just looked at the magnitude of this, E2 is equal to E1 cosine theta. So this is just going to tell me how strong the electric field is before and after. But let's say I don't want to know the strength of the field. Let's say I want to know how bright the light is. Well, the brightness, which we'll call I for intensity, which is brightness, which is proportional to power. Well, we know the power is proportional to E squared. So the intensity is proportional to E squared. So the intensity of the light afterwards divided by the light before is going to be equal to E2 over E1. But that's just squared. So this is, so E2 is E1 cosine theta, all squared, over E1 squared. And that's to say cos squared theta. So that is what we're going to call Malice's law. So this is the intensity after I have a filter. This is the intensity before I have a filter. If I have polarized light, this is the intensity of the light of the polarized light. This is the intensity of the polarized light after the second filter. And this is the angle between filters. Right? Because it doesn't actually matter that the second filter is along the x direction. That's just a direction I chose to make it easy to do the math. What I really care is what the direction is between the first slit that makes the light move in the one direction and the second slit, which makes the light in the second direction, and that's the angle theta. So this tells you how big it is. And if we had been doing this course without COVID-19, you would do this experiment in the lab. You would actually measure this. Now you probably could. I'm actually thinking you could probably find an iPhone app that measures light intensity and actually map out the thing. We thought about doing it, but it's not really worth it. But what this tells you is that it doesn't change evenly, right? And you can sort of see this if you watch it. There's a sort of a rapid change in different places. It also tells you where the halfway mark is. If I want this to be 1/2, it means that that's cos squared theta, which means that cos theta is 1 over root 2. And what's the angle that gives you a cosine theta of 1 over root 2?
$60 degrees?
No, it's 45 degrees. 1/2 is 60 degrees, right? But 1 over root 2, that's the 1 over root 2 is the 45 degrees. So if I have my two filters at exactly 45 degrees, then I have half the light coming out. This is useful for all sorts of things. One thing in particular, now I should point out, this is entirely wave-like behavior. This is one of the proofs that light is a wave. And incidentally, a very good question I might put on a final is list some pieces of evidence. That's how we know that light is a wave, right? This is wave-like behavior. It has to have something, a transverse component in order to do this. And if light was made of just little pellets that we're shooting, which is what Newton believed, Isaac Newton believed that a light was made of these corpuscles, then it wouldn't have this characteristic, or they'd have to be very strange corpuscles. Now, of course, the real story is a little bit more complicated than that, but it's still, this is a very powerful proof. So this is aligned vertically and this is aligned horizontally. Right, it's going to be this guy because these guys are almost the same direction. So I'm going to maximum light output of this. And which one's going to be minimum? Yeah, it's going to be that one. So for that guy in the maximum, what's the direction of the light coming out of the second polarizer? Like I said, this is easy stuff. We're on the other side of the mountain, right? This is not as hard. So yeah, so this is going to be oriented this way. It's going to be oriented in the same direction as that filter. Okay, now maybe you guys know this from the reading and maybe not, but here is the fun one. I'll wait for an answer from everybody. I'm seeing some A's. I'm not seeing any B's. I'm seeing a B. Okay, just because taking the other bet, it's good odds, right? Everyone else answers A, you look really smart if it's B. I approve. No, okay, you just don't know. Well, here's the thing. So let's just walk it through. So A is the correct answer. We'll see in a second. This light, after it comes out of this, is polarized vertically. So it hits this thing, none of the light can get through because only horizontally polarized light makes it through. But in this case, the light comes out of the first one polarized vertically, and it hits the second one, some of the light makes it through. Less light than before, but some of the light makes it through. In fact, if this is at 45 degrees, half of the light will make it through. Half of the energy of the light will make it through. If then after the second polarizer, the light is now diagonal. So now it hits the third polarizer. And again, it's a 45-degree angle. So some of the light makes it through, about a quarter of the light. And so you can do this. If you have your little bit of stuff, you can go through this exercise because you can cut it into quarters and make 4 pieces. Or cut it into thirds if you can figure out how to do that, right? So there's the first piece. That's aligned the same way. That's aligned so that I'm getting very little light coming through. Now I'm going to take the third piece. And of course, the third piece, if I put it on top, I can just block some light. But if I put it in the middle, it lets more light through. So the third, it's a filter that makes more light come through. It does this entirely by blocking, not by creating light.
Does it change the direction of the light coming through?
That's the point, is the polarizer changes the polarization. It doesn't just reduce, it changes as well. And so this means, which is the whole point of that previous question, where does the light come out vertically or light slanted? It comes out slanted out of the second one, and so then some of it can make it through the third one. This, I think, is like one of the coolest things in the world. This is so neat. By putting something in,
does it like fully change, or is it just like that component is all that can move through that way, or is it all of it is turned that direction?
Yeah, so that's the thing, is what makes it through. So it does both things. It filters it, so it takes off. So if I take this component, it takes, that's the before. It reduces it to the length of this, and this is bigger than the length of this. But it also changes the direction in which it's polarized. So it does both things. In reality, it doesn't pick, it's a little bit fuzzy as it picks a couple of different directions. It's not just one exact direction. And that's why you get a little bit of light through even when you have crossed polarizers. They're not perfect. But the principle remains the same, so the polarizer doesn't just reduce it, it also changes it. This is a really important thing. This turns out to be massively important when you get to quantum mechanics. It turns out all of quantum mechanics works this way. If you're making a measurement, changes the system. this is a really important point and a really interesting one. So what if I put in more than one? So the right answer here, I think so it's not no light, because if you think about every step of this, Stephen, right? You start off like this, and so the idea here is that each polarizer is just a little bit different from the other one. So we have the first one's like this, and the second one's like this, and the third one's like this, and the fourth one's like this, and the fifth one's like that, right? So the first, second, third, fourth. If you're going between the first one and the second one, only changes the light a little bit. And this angle in here is very small. So cosine theta, cosquared theta is very big. And so a lot of the light makes it through. And now the light is polarized like this. And then it hits the next one. So again, there's a small angle between them. And so most of the light makes it through. And in fact, in every step, the same proportion of light will make it through. It's the same angle between each polarizer. So a lot of it will make it through. And in fact, if you set n to be very large, so I have a very large number of these, you can get almost all of the light through, because every single step is reducing it only a tiny amount. And so you can gradually change the polarization of the light from horizontal to vertical if you have many, many of these, which is very, very cool. Oh, I didn't show you the other one. I've got my demos here.
I guess this one just doesn't make sense to me from a different standpoint of, like, I understand it to a degree, but this one's just like doesn't make sense from it's not what you would logically think would happen. Eventually you would think you'd lose all the light.
Yeah, well, yeah, that's right. But it's because each absorber is doing very, very little. And the closer you make them to each other, the less they're doing. Right? So here's the example. So natural light that's coming from a light bulb, is in fact randomly polarized. It's actually polarized in all directions. Each little bit of the light is polarized a different way. If it goes to the first polarizer, it's only polarized one way. So in this case, it'd be it's vertical up and down. Now, as I rotate that polarizer, you see what it puts out is reduced in size, but also in direction. So that's at 90 degrees where there's nothing. If I keep going, I get the full output again.
Not asking about 90 degrees. I thought it was saying that they were all at 90 degrees from each other.
No,
so
it's
that's why I
saying they're
thought about
going. Yeah, no, sorry. Yeah. So that's a reading thing. Is let's see, stop, share, start, share screen, advanced, camera 2. Okay. So each time rotating the axis of polarization over an angle of 90 divided by n. So if I had 10 of them, each one would be 9 degrees. So 9 degrees, 9 degrees, 9 degrees, 9 degrees, 9 degrees, 9 degrees, 9 degrees. So it's a thickly worded question.
The way that I was thinking about it that I think might help make some sense to other people is it's almost like a car turning a corner. Like if a car's trying to turn a 90-degree corner, it's going to lose a lot of speed. But if you're turning a car at 9 degrees at a time, you're going to keep a lot of the speed. You might not even have to slow down at all.
Right. That's not a bad analogy. It's the same idea. Is the energy that the amount of which you're changing energy is very small. I quite like that analogy. Actually, I might use that. Thank you. That's basically all there is to it. There's some questions on polarization in your homework to tell this out. I'm going to add one detail since we have just a couple of minutes. I think it's worth sharing just one more little bit with you that's kind of interesting. And that is that this is not the only way we can arrange, whoops, I don't want that. It's not the only way we can arrange the light to be polarized. There's in fact another way we can do it, which is kind of neat. And incidentally, all of these demos are available at otterbein-physics.github.io, which I think is linked to somewhere. So if you ever want to go through these and just play with them, they're all here. But here's a nice little demo I made up. So what I've got here is the green and the blue are two waves. One is polarized horizontally and the other is polarized vertically. Now, because of the superposition principle, if I were to shine both of these rays of light in the same place at the same time, the electric fields would add. And you would get the thing on the bottom. This is like adding a vector that's horizontal plus a vector that's vertical, and you'd get a horizontal wave. If I change the amplitudes, say, of the red one, it means that it moves left to right less. And if I increase that amplitude, it's moving left to the right more. So in fact, I can add linearly, like vectors, these guys to add them up, which is kind of neat. But another thing I could do is I could change the relative phase. So I could shine this green and the red lights, and I could change it so that the phase of the green light is different from the red light. And if I do that, so this is in phase, and now I've changed them so they're out of phase, I can get a circular pattern. So this is now the green and the blue are 90 degrees out of phase. And so when one is up, the other one's in the middle, and when the other one's in the middle, the other one is down. And so you can get this happening. Or I can get it going the other way. Let me see if I do that. This is called circularly polarized light, which is kind of a neat, thing. And this is actually used in lots of different ways. For instance, you shine light through sugar water. Sugar is a chiral molecule, that is just to say it twists in a certain direction. And so if you shine light through a sugar molecule, it comes out, I believe, right-handed. The light is polarized in the right-handed direction. If you shine it through like the chiral antithesis of sugar, which is like aspartame, then it comes out left-handed. So we don't have time to get into the math or get into the details of this, but this just points out there's actually a whole bunch of rich phenomena here that's not just the vertical and horizontal polarization. So there's cool stuff going on there. Polarizers show up, just a regular linear polarizers show up in a couple of different places. One is that if you shine light on a surface, so if you have light glancing off a surface, the light tends to come off polarized horizontally. So if I shine light on a shiny surface like water, the light, when it reflects off, will tend to be more horizontal polarized than vertical polarized. Now, if you're driving, that could be light reflected off the road hitting your eyes. Or if you're fly fishing or something and you're sitting in the water and you're looking out at the water, that light that's reflected off the water coming from, say, the sun. So if you're like looking into the sunset, there's this bright patch of water in front of you. Now, let's say you want to look into that water. You don't want to be blinded by that bright patch. What you can do is you can take a piece of polarizer and clip it over your eye so that it cuts out the horizontal component and only leaves the vertical component. Those are polarizing sunglasses. We use them all the time. They cut out glare. And you should try this yourself. Take your little piece of polarizer and look at like a shiny floor or something like that, or a shiny surface at incident angle. So for instance, if you have what we do at Otterbein is I take you out to the long hallway and say, look at the floor 20 feet away from you and see the light coming from the windows. And if you rotate it one direction, you can cut that glare straight out. And that's why these are great for driving or other activities. They cut out glare. They cut out that reflection that comes off of surfaces. And so you can see better because you don't have this bright stuff in your eyes. So polarizing sunglasses are better. I think I have a pair. And you can do this. You can see if your sunglasses are polarizing by taking your sunglasses. Let's see, where's my light here? And I can share. New share, advanced, second camera. All right, so here's my polarizing sunglasses. And if I hold this over, I don't know if you can see this. You can see that the sunglasses are indeed polarized in one particular direction. They're polarized in the horizontal, in the vertical direction. So this comes up actually in a lot of different places, polarization. Another thing you'll notice if you play with the laser pointer in your kit, you'll notice the laser is polarized. Laser light is frequently highly polarized. Not 100% polarized, but actually very polarized. And so this allows you to play all sorts of cool games with light that lead to some really interesting conditions. So physicists who work in optical conditions make heavy use of polarization in understanding how systems work. Okay, so that's enough for today. Next time we'll talk about more wave natures. I'm actually not going to follow a textbook. I'm going to bounce back and forth because it makes more sense considering our truncated schedule. So next time we're going to talk about interference, another wave effect in light. And then next week we'll talk about geometric optics, about refraction and reflection and maybe a little bit of lenses. And that will be the course. So I know I was a lot of talky today. I'll try to make it less talky next time. And everybody have a good one. Remember, homework's due on Friday. Let me know if you have any questions. I'm available on Thursday if you guys want some FaceTime on Zoom or something like that. The next lab is due next Thursday, and the final assignment will be due the Monday of exam week. Okay. Hang in there. We're almost through this. The end is in sight.